5 key insights from recent quantum mechanics research. 1. Branching emerges naturally. Simulations by the University of Barcelona show that classical reality and branching into multiple worlds emerge naturally from standard quantum mechanics without the need for wave function collapse or conscious observers. 2. Probability explained by amplitude. The research resolves the probability problem in many worlds by demonstrating that high-amplitude branches are more likely to be observed, aligning with experimental quantum probabilities. 3. Decoherence times confirmed. The simulations confirmed that quantum systems decohere almost instantly when interacting with their environment, explaining why we don't observe superposition in everyday life. 4. Arrow of time from branching. The branching structure itself creates a natural arrow of time, as the wave function becomes more complex and branched over time, mirroring the increase in entropy observed in classical physics. 5. Testable predictions for quantum computing. The research suggests that quantum computers exploit the multiverse S structure by creating branches where different calculations occur, making specific decoherence patterns testable in laboratory experiments. The research conducted at the University of Barcelona in 2025 represents a significant milestone in our understanding of quantum mechanics and the many worlds interpretation, MWI. Here's a summary of the key findings and their implications. Key findings. 1. Branching emerges naturally. The simulations demonstrated that classical reality, characterized by distinct, non-interfering states, naturally emerges from the mathematics of quantum mechanics without the need for an additional collapse mechanism. This branching occurs automatically when a quantum system interacts with its environment, which is typically composed of many particles. 2. Decoherence and non-integrability. The team focused on non-integrable systems, which are chaotic and follow random matrix theory rather than simple patterns. They proved that such systems naturally produce branch splitting, where quantum superpositions rapidly decohere into distinct branches. 3. Branching rates. For a system with just 10 particles, the number of branches created during an interaction can exceed 1,000. In complex systems like human brains, which contain trillions of particles, the branching rate is astronomical, possibly billions per second. 4. Probability in MWI. The simulations showed that certain branches are more probable due to having more amplitude in the universal wave function. This resolves the probability problem in MWI by explaining why we observe quantum probabilities. Our subjective experience samples the multiverse weighted by amplitude. 5. Arrow of time. The research indicated that branch splitting creates a natural arrow of time. Before branching, the wave function is simpler. After branching, it becomes more complex, which appears as increasing entropy within any single branch. 6. Quantum computing. Quantum computers exploit the multiverse S structure by creating branches where different calculations occur. The final result reflects interference between these branches, effectively harvesting computational work from parallel realities. Implications. 1. Theoretical physics. The research provides strong theoretical support for MWI, showing that it is not just a philosophical interpretation but a natural consequence of the Schrödinger equation. It suggests that many worlds are implicit in quantum mechanics and do not require additional assumptions. 2. Empirical testing. The simulations make testable predictions about decoherence patterns in isolated quantum systems. Laboratory experiments can measure these patterns to further validate or refute the MWI. 3. Philosophical implications. If confirmed, MWI would fundamentally change our understanding of reality, suggesting that every possible outcome of a quantum event actually occurs in some branch of the multiverse. This has profound implications for concepts of determinism, free will, and the nature of existence. 4. Technological applications. The insights from this research could lead to advancements in quantum computing and other technologies that exploit quantum phenomena. Understanding how branching occurs could help in designing more efficient quantum algorithms and error correction methods. Future directions. 1. Experimental verification. Conducting more detailed experiments to measure decoherence patterns and confirm the predictions of the Barcelona simulations. Developing new techniques to isolate quantum systems for longer periods to observe their behavior. 2. Theoretical extensions. Exploring the implications of MWI in other areas of physics, such as cosmology and black hole information paradoxes. Investigating how branching affects our understanding of time and causality. 3. Interdisciplinary research. collaborating with philosophers, computer scientists, and engineers to explore the broader implications of MWI. Developing new educational materials and public outreach programs to explain these complex ideas in accessible ways. The research from the University of Barcelona represents a significant step forward